Okay, we've got a few systems here and a couple of pictures, then I'll explain what these mean. And I'm trying to keep the camera in focus, so let's see if I can. Okay, now, if I take this first equation, 2x plus 3y equals 8, I can graph the thing. X-intercept occurs when y equals 0, 2x equals 8, that means x equals 4. So this point out here is going to have a coordinate of 4 on the x-axis. I'm not going to write all the coordinate pairs in interest of time. You can easily graph these yourself. And then if x equals 0, y equals, well, 3y equals 8, y is going to be 8/3. So right there's 8/3, about 2 2/3, a little more than half and 4. Don't know if I've got that quite right, but here's 8/3 on the y-axis, and here's straight line more or less through those points. If I graph this one, my x-intercept, y is 0, 6x is going to be 20, so x is going to be 20 over 6. It's about 3 1/3. I'm not going to label that, but I'll use a different color for this equation. Somewhat less than 4. And if 9y equals 20, which occurs if x equals 0, giving you the y-intercept, it gets us a little over 2. So it's going to be a little less than this. So now if I draw a straight line between these points, I get something like this. That's not completely clear from the graph, but these two lines are parallel. If you solve for y, you're going to find that y equals negative 2/3 x plus 8/3. If you solve this for y, you're going to get y equals negative 6/9 x plus 20/9. 6/9, the slope here, negative 6/9, is the same as slope here. Did I say that right? Yeah, is the same as the slope here, which is negative 2/3. Negative 6/9 equals negative 2/3. I'm not going to write that out. I'm just going to say, use your basic pre-calculus, solve both of these for y, and you'll see that the slopes are identical. So you should do that. And you should also, sketch a graph. Now, what happens then if we try to solve the system of equations? Well, we could do -3 times the first equation, which would give us negative 6x minus 9y equals negative 24. And we just take the second equation, 6x plus 9y equals 20. We add them up. Well, negative 6x and 6x is 0, negative 9y and 9y is 0. So on this side we get 0, on this side we don't. Okay, so this is an untrue statement. This means that we don't have a solution. So this means that there's no solution. And if you use the terminology of your text, which you have read, this is inconsistent. Means we have an inconsistent system. Okay, now let's do the same thing down here. Well, the first equation is the same. So, here's 4, and here's 8/3. Okay, now we let y equal 0, and 12x equals 48. Well, 12 goes into 48 4 times. And if I'm talking too fast, just solve the equation. Write down what I'm talking about. Okay, the x-intercept is clearly 4. It agrees with what we have here. The y-intercept, let x equals 0, you get 18y equals 48. 48 divided by 18 is 48/18. We have a common denominator that could reduce down to 24/9, which in turn could reduce down to 8/3. And by darn, that's our y-intercept here too. So the x and y-intercepts are both the same. So that these graphs are identical. we get the same line. Okay, well, 2x plus 3 plus 8 and so forth. We reduce this, and what do we get? Okay, well, let's just multiply by -6 up here. -6 times your first equation gives you -12x minus 18y equals -48. The second equation gives you 12x is 12x plus 18y equals 48. If you add these equations, you get 0 equals 0. This is consistent. Okay. Solutions exist. What are the solutions? Well, the solutions consist of all the points on either line. Okay, so solution set is just the equation. Let's just take the first equation, it's in lowest terms, 2x plus 3y equals 8. Or we have a free variable. In either equation, since they give you the same line, we could pick either an x or a y. And its value, we could assign any value, making that a free variable. So let's just say we're going to pick y to be the free variable. We could pick a value for y here, and then it's going to give 3y a numerical value. We're going to be able to solve for x. So having picked y, we can find x. And if we pick whatever we pick for y here, if we use it in this equation, it's going to give us the same x. Now you need to convince yourself of all that. But as we saw in class, this can be parameterized. Not leaving myself enough room here, but I often do that. We can say that the free variable we could use either x or y as the free variable, but usually use the second term. We usually don't use the variable in the leading term as the free variable. Free variable y equals t, so that x equals -2/3 t plus 8/3. Now we've talked about this in class for the system of equations of two variables. So hopefully we understand what I'm talking about here. And of course, your text has numerous examples, at least an adequate number of examples. Okay, now let's move on to an equation in three variables. Okay, so we've got 4x plus 6y plus 8. Well, I'm not going to read it to you, you can read it. Okay. Each of these equations represents a plane in 3 dimensions. What's the plane? Well, here we have x, y, and z axes. And just to be sure, x goes this way, and y goes this way, and z goes this way. Not writing those real carefully. And we can find the axis intercepts along all 3 axes, as we did in class. I'm going to do this pretty quickly. If y and z are both 0, that puts us on the x-axis. And of course, 4x is going to equal 48. X is going to equal 48 divided by 8, 12. So right there would be the point 12, 0, 0. Yeah, we want to do the coordinates. I'll actually write the coordinates here, just for one of these. If x and y are 0, then we're on the y-axis. So 6y equals 48, which means that y is 48 over 6, which is 8. So we're going to have the point here, x is 0, y is 8, z is 0. And then if x and y are both 0, z is 6, giving us the point 0, 0, 6 on the z-axis. Okay. The second equation here gives us something that looks like this. Well, let's go back. Once we have the 3 points, we can just draw the triangle connecting those 3 points and kind of shade it so we can see the orientation of this plane. So it's kind of oriented like this. Okay. This one is what we get here. I'm not going to go through the details. You can do it yourself. Let y and z equal 0. You're going to get x equals 6. Let x and z be 0. You're going to get y equals -10, which is what puts you over here. And let x and y equal 0. You're going to get z equals 7.5, which gives you a point up here. They're not graphed real accurately, but what we then have is a plane kind of like this. Okay. And let's see. Yeah, something like this. So we have a plane that goes like this and a plane that goes like this. They meet. Those 2 planes I showed you these small planes. These are a little harder. Not to hold up, to get my hands around and demonstrate what I want to demonstrate. I don't have a hand left to gesture with. But okay, here's this plane. And here is this plane, kind of in this direction. So these 2 planes meet along some line. They don't meet at a point. Now they do meet. Okay. Now 2 planes don't have to meet. It could be kind of like this, except you got 2 planes that are in the same direction. Either they're the same plane or they're separated by some distance, but they're parallel. Okay, so you can have parallel planes. Parallel planes can be consistent either by parallel planes can be consistent if they coincide, if they're the same plane. They're inconsistent if they don't have any common points. If you got one common point on 2 parallel planes, all the points are common. Think about that. Okay, so here we have 2 planes. We expect that if our picture is right, that the 2 planes intersect along a line. So now we don't have a lot of room to do this. So I'm not going to write exactly what I do. I'm going to multiply the second equation by -2 and add it to the first. Okay, so I'm just going to do this. -2 times the second equation plus the first. Okay, I'm not going to write them out. I'm just going to do it in my head, which means I'll probably make a mistake, so you just correct me. Okay, well, -2 times the second equation is going to give us -10 for the x. Added to the first equation, that's going to give me -6x. -2 times -3 is 6. Added to the 6 here, that's going to give me plus 12y. Now, -8, -2 times 4 gives me -8. Added to the 8, the z's go away. That's why I chose -2. I wanted z to disappear from my equation. And then -2 times 30 is -60. You add that to 48, you have -12. Well, what's this? That's a linear equation in 2 dimensions. And if you understand how to parameterize it, we see that we've got a free variable, a single equation in 2 variables means that we have a free variable. So again, we let y equal t, so that x equals (2t plus 2). If I did my arithmetic correctly. we solve this for y, we get 12y. Oh, I got it wrong. Not solving it for x, solving it for x. Got it right. Okay. We get negative 12 minus 12y. We divide that by negative 6. We get 2y plus 2 or 2t plus 2, since we're letting y equal 2. Again, when the use of the parameterization is, then we just plug different numbers for t in here and very quickly calculate a set of x and y coordinates without having to solve anything. Okay. These are consistent because you have solutions and you have infinitely many solutions, just as you do down here. You have a solution for every value of t. Here you have a solution for every value of t. A set of numbers x and y that satisfy the equation. And yeah, that satisfy both equations. It doesn't matter what z is. Okay. And gee. Yeah, I should have finished it. I've got to figure out where to write things. I'm going to pause for a second. Okay, I misspoke a minute ago. I actually said it doesn't matter what z is, but the value of z is determined by the values of x and y. Okay, and what I didn't have room to write is what you do with that. Don't have to rewrite everything. So I'm just going to say, and your book will have examples. Let's just take the second equation and solve it for z. Z equals what? It's going to be negative 5 x plus 3/4 y plus 15 halves. Now we're parameterizing in terms of t. So to find z parameterized in terms of t, I'll just come up here. I'm going to borrow some space and let this run over. Z then would be negative 5/4 x, which is negative 5/4 of 2t plus 2. Y is equal to t, so 3/4 y is 3/4 t. And then it's plus 15 halves. And of course, we can simplify this. We can distribute the 5/4 through here. We're going to get negative 10/4 t, which is negative 5 halves. Well, we'll use fourths because this is going to be fourths. So we have negative 10/4 t plus 3/4 t is negative 7/4 t. And then we have negative 5/4 of 2, which is negative 10/4 or negative 5 halves, and 15 halves. Okay, negative 10 halves and 15 halves is 5 halves. So there's your expression for z. And now, take any value of t, plug it in here, plug it in here, plug it in here, and you have coordinates of a point x, y, z on the line of intersection between these 2 points. Okay, so once more, having 2 equations and 3 variables is going to give us if we have a solution, is going to give us, okay, if you have two equations and three variables, it's possible that these equations describe the same plane. Okay, in which case you have an infinite number of solutions. It's also possible that they describe parallel non-intersecting planes, in which case you're not going to have any solutions. In the first case, the equations would be redundant, so you'd essentially only have one equation. That's the case where the two planes are the same, and you would need two free variables. Not going to talk about that right now. In the more general case, where the two planes intersect on a line, then you do have a free variable because you get a solution. It looks like this, and you're free to choose either X or Y. When we parameterized it, we chose Y equal to the parameter T, and we got them the parameters, the parametric equations for X and Z. Okay, well, that's the general case. If you have two equations and three unknowns, you're going to be able to eliminate one of the variables. And that's going to give you, if you have non-parallel planes, that's going to give you an equation in two variables, equation of a line in the XY. You can parameterize that line and then use one of the equations to figure out what Z is in terms of X and Y, and plug the parametric equations for X and Y in for that Z. They've got to follow that step by step. You got to do that in order to really understand the process, and you want to think about what it means. Okay, you might not be real good at visualizing where the planes are, but I do recommend you try to sketch them. Okay. Now here is a system of three equations. Okay. The first two equations are the same as these. They give access to make it easy to solve. Okay, so we don't have to do a whole lot of work. Again, if I do -2 times this plus this, I get -6x plus 12y equals -12. I can eliminate Z between this equation and this equation by just adding -4 times this equation to this one. So -4 times the third equation added to equation 2 eliminates Z, okay? -4x added to 5x gives us x. -4y added to -3y gives us -7y. And -4 times 5 is -20 added to 30 gives us 10. That's the equation of two lines in the XY plane. And let me back up and observe that this equation can be represented by this plane. So you've got this line of intersection between these two planes, and you've got this plane, and that line of intersection goes through this plane because this plane isn't parallel to either of these. Now we can finally solve the system of equations. We do six times the second equation plus the first, and that's going to get rid of x. 6 times -7 is -42. We add that to 12y, we get -30y. -6 times 10 is -60. And add that to -12, we get -72. So we get y equals -72 over 30, which is -12 over 5. Now we can take this value, plug it into this equation, and solve for x. Okay, we would get 84 over 5 here. 10 is 50 over 5. Negative 34 over 5. So maybe use a question mark there. I don't know if that's right or not. You can solve it and figure it out. Okay, and now we've got a value of y and a value of x. We can plug it in up here. And we can get the value of z. I'm not going to do that in my head. I'm probably wrong about this one. Even more likely I'd make a mistake there, even if I'm right here. We conclude that this system is consistent. With exactly one solution. The system up here was consistent, but there were infinitely many solutions. And the infinitely many solutions are all the points on the line. Every point on the line that we parameterized here is a solution. There are infinitely many points because there are infinitely many values of t that you can substitute to get points on the line. Okay, now we're going to look a little more at a little more systematic way of solving an equation in 3 variables. What we've done, well, never mind. I was going to say what we've done up to here, pretty much a repeat of what we expect people to bring to the course from their algebra courses, except maybe for the parameterization. And that's something that I don't think is usually covered in secondary algebra courses. Although, well, yeah, and it really isn't covered in the community college curriculum until the end of the calculus course. So there's no reason anybody should have known in advance how to parameterize straight lines or surfaces or anything else. Okay, this course, everything's straight lines and planes and hyperlines and hyperplanes. We'll talk about what that means later. In transferring, I want to be more systematic about how we solve a system of equations. I just kind of went by hook or by crook and just picked multiples of equations that would accomplish what we want to accomplish. In linear algebra, we generally use a much more systematic way of doing this. To transfer this equation onto this board, which wants to sit right over this equation, I copied down the essential numbers in the equation, 4, 6, 8, 48. I know that this is going to be my multiple of x, this is going to be my multiple of y, this is going to be my multiple of z. It's going to be equal to this. Same for each of the other 2 equations. You can check that out. Okay. Now, turns out that in general, I just take those numbers and put a little dot here, or a dotted line here, to indicate that this is what we call an augmented matrix. We'll see how to use this augmented matrix. And there's a lot of notation and terminology around matrices. But what I'm going to do is pretty straightforward, okay? I'm going to take the system of equations now, and I'm going to write it out. To write the system of equations, since I've got the matrix, I can see exactly what I should be writing. Okay. This corresponds to this equation. Okay, so now we're going to say this means exactly the same thing as this. Now I'm going to do another thing. And I actually intended to do that, and then I got tied up in what I was saying. I don't want to use X, Y, and Z anymore. The reason is we can have equations with way more than just 3 variables. And in general, in linear algebra, instead of using X, Y, and Z, and of course, X, Y, and Z is perfectly okay, but to get used to the idea of subscripting variables, instead of Y, we're going to use X2, instead of Z, we're going to use X3. I hope this won't be confusing to you, but if you've read your text, you've already seen the notation. So instead of X, Y, Z, we're going to use X1, X2, and X3. Okay, well, just kind of follow along with what I do. I'm going to rewrite the system. I want to have X1 plus X2 plus X3 equals 5 as my first equation. And of course, changing the order of the equations isn't going to do a thing to the solution. Okay, solution is going to be the same no matter what order the equations are in. Okay, then I'll put my 4x1 plus 6x2 plus 8x3 equals 48 as my second equation. And my x1 plus x2 plus x3 equals 5 as my third equation. And over here, we're going to do the same thing to the matrix. Matrix just reflects what we're doing over here. And ultimately, we're going to end up just using the matrix and treating each of these as just each row of the matrix as an equation in a very straightforward and obvious way. Okay, so now I'm going to rewrite my 3 equations, but I'm going to do an operation to each one. I'm going to put x1 plus x2 plus x3 equals 5 here. And, you know, so you're getting used to me making clerical errors. When I wrote down the third equation, I just copied the third equation from up here. And of course, I'll do the same thing here. So let me correct it. Okay, third equation should be this equation. We can't throw out one of the equations. We've got to represent all the equations if we're going to get the solution to the system. Okay, I think we're good now. Okay, so here's our first equation. Now, the second equation, and I'm not going to go through the details, which means I'll probably make a mistake, but you'll understand what's going on. Okay. I want to wipe out this x1 in this equation, and this x1 in this equation. Now, of course, I can't just wipe them out. I can't just say they're gone. I've got to do it using steps that'll preserve the solution set. In other words, whatever I do can't change the solution, and I would change the solution if I just got rid of the 4x1 and the 5x1. To get rid of the 4x1, I'm going to add -4 times the first equation to the second. That's perfectly legitimate because I'm adding multiples of the equations. I'm not going to change the solutions to the system. So I do -4 times the first equation plus the second. I hope you can read that. But so -4x1 added to 4x1 gives me 0. -4x2 plus 6x2 gives me 2x2. -4x3 plus 8x3 is 4x3. And -4 times 5 is -20 added to 48 gives me 28. Then what do you think I'm going to do? Get rid of 5x1. You should be able to predict it. Think about it for a second. Anyhow, hopefully you thought about it. If you haven't, you can pause the video, think for a minute. I really strongly recommend that you do these such things. Okay, so we're going to do -5 times the first equation plus the third equation, which is going to give us 0 here. Now, -5x2 minus 3x is -8x2. -5x3 added to 4x3 gives us -x3. And -5 times 5 is -25 added to 30 gives us 5. Now, this is progress. Okay. Now we're going to do a couple more steps. And you're going to see, actually, we just need one more step. And this system is going to be in upper triangular form. So we can easily solve it by back substitution. Now, look, what we're going to do is we're going to add 4 times this row to this row. That's going to get rid of the -8x2. We're going to have a 0 here. And then we have an upper triangular system that's easily solved by back substitution. Okay, but let's see what we would do with this matrix over here. Okay, well, let's see. I want to get an upper triangular matrix down here. I want to get rid of the 4, the 5, and the -3. I want those all to be 0. And then I'll have something that represents an upper triangular system of equations that I can solve by back substitution. The steps are identical to the steps I would do here. In other words, if I add a multiple of a row to another row, I'm just going to be adding the coefficients of x1, x2, and x3 and the number to the right of the 0. Multiples of those coefficients to the coefficients of another equation, which is essentially what I just did here. It's really kind of redundant to keep writing x1, x2, and x3 if I just keep track of where these numbers are. Okay, well, if I do -4 times the first row plus the second, -4 times the first row is going to give me 4, 4, 4, 20. Sorry, -4, -4, -4, -20. Okay, well, -4 and 4 gives me 0. -4 and 6 gives me 2. -4 and 8 gives me 4. -20 and 48 gives me 28. So multiplying the numbers in the first row by -4 and adding to the second row gives me a row that perfectly represents the second equation here. Then multiplying -5 times the first row, giving me -5, -5, -5, -25, add to the third row, giving me 0, -8, -1, 5. The same numbers that I have here. So it's easier to write. It's easier to see the form of the equation if you have it in this form, the form of what we call an augmented matrix. Well, now let's just go back to the equations, even though if we're really catching on to this, we can say, let's just deal with the augmented matrix. Well, that's what we normally do, but we're not going to do it yet. Okay, so still have x1 plus x2 plus x3 equals 5. We have 0 plus 2x2 plus 4x3 equals 28. And then we're going to add 4 times the second equation to the third equation. Okay, well, and that's so that the 2x2 will become an 8x2, which added to negative 8x2 is going to be this, give me the 0 that I want here. Okay, and negative 4 times 4 is negative 16. Subtract 1, you get negative 17. And negative 4 times 28 is negative 112. That's getting a little big. Yeah, those are the kind of big number here. And let me make sure that I'm. Yep, that's what I'm doing. Negative 112 added to 5 gives me negative 107. There's no reason to expect this to come out with nice fractions. I just made these numbers up. You know, wasn't trying to make it easy. Okay. Usually it isn't. Okay, so here we have this. Now we understand that, okay, we can now solve for x3. It's going to be 107 over 17. Then we plug that in for x3 up here, getting us a number, and we can solve for x2. And now we know x3 and x2, we can plug them in here, giving us 2 numbers. And the only unknown we have is x1, and we can easily solve. Now, if we do this, to the numbers in the row, we're going to take 4 times these numbers. I almost saw 128 here instead of 28. Gotta be careful to make those dotted lines look like dots, not ones. Okay. So 4 times this row is going to give me 4. You're going to give me 8, 16, 112. So 8, 16, 112 added to negative 8, negative 1, 5. 8 and negative 8 gives me 0. 16. Uh-oh. Screwed up over here, didn't I? Okay, I should have added 4 times the second row to the first. I did negative 4 times the second row. So I have the wrong numbers here. So it's a good thing I'm doing this 2 different ways. I can catch at least some of my mistakes. You understand I'm only pretending to make these mistakes so you won't feel badly, right? Okay, well, you'll make some. Okay, it's not a negative 4 that I'm adding, it's a negative 4 times this that I'm adding, it's 4 times. So that's going to be 16 and minus 1 is negative 15x3. And it's going to be plus 112 added to 517. Okay, now let's go back here again. 4 times this row gives me 4, 16, 112. Added to negative gives me 4 times this row gives me 8, 16, 112. Added to negative 8, negative 1, 5. Negative 8, negative 8 is 0. 16 and negative 1 is 15. 112 and 5 and 117. Okay. And it's not negative. Now everything agrees and would have in the first place if I had done everything more carefully. Okay, so now back substitute to get the solution. I'm just curious. Yeah, it's conceivable that I got the right solution up there. Okay. The solutions that we get here should be identical to the solutions we get if we start with y equals negative 12 fifths, x substitute here, and then substitute in one of these equations. But this is a little more orderly. Okay, what we've just done is called Gaussian elimination. So this was Gaussian elimination, just adding multiples of rows to other rows. There are a couple of other operations we can do. We multiply a row by a number and so forth. We're going to do that in a minute. And it leads to essentially back substitution with equations that looks like this, with matrices that looks like this. And every matrix here just represents one of these equations in a very straightforward, simple manner. I'm going to go a little further now. Okay, here we have the system that we've reduced by Gaussian elimination. And I'm not going to do the equations anymore. I'm just going to do the matrix. So we have matrix 1, 1, 1, 5. First row. Second row. Now it's 0, 2, 4, 28. Gauss-Jordan or Gauss-Jordan, the way it was pronounced when I was in graduate school, I have no idea if it's being pronounced right, but it's not the English Jordan. The guy was European. I forget what his nationality was. But anyhow, I want ones here, here, and here. Okay. You understand it's going to be very convenient to have a 1 here, for example, because then the equation just represents 1x3 equals whatever it equals. And I wrote that as an x cubed. Caught that out of the corner of my eye and almost said x cubed over here. Okay. If I have a 1 here, well, just divide everything in the equation, every coefficient by 15, and I'll get 117 over 15. That is my value of x3, as we can see from here. If I have 117 over 15, then I've got my solution already. Anyhow, I want a 1 here, I want 1 here, I want 1 here. I can get that easily. You could take this equation and divide it by 2, it wouldn't change its solutions. Okay, so I'm going to take this row and divide it by 2. So I'm going to say the second row divided by 2 is 0, 1, 2, 14. Divide those numbers by 2. Get it. I'm going to do the third row. Divided by 15. Give me 0, 0, 1. 117 over 15. Okay. So I already know what x3 is because this row represents the equation x3 equals 117 over 15, which I said over here while I was waving my hands, but that's what it is. Okay. Now, I've got a 1 here. I can wipe out the 2 and the 1 here by adding multiples of the third row here and here. And I'm going to actually try to do that accurately. Numbers like that, but eventually I'll probably give up. I mean, I can do it, but I don't want to stand here doing a bunch of calculations and checking them on your time. You can easily do the calculations yourself. Okay, well, what I'm going to do then is I'm going to take -2 times this third row and add it to the second row. And my third row is 0, 0, 1, 117 over 15. Look, 117 a little high, but okay. Okay, if I take -2 times that and add it to the second row, -2 times 1 is -2. I add it to 2, I get 0. Well, what do I get over here? I get -2 times 117 over 15 added to 14. I want a little more room there. Okay, so I'm going to get 14 minus 234 over 15. Now that isn't particularly hard to calculate. 15 times 14 is 210. So 14 is 210 fifteenths. So I get negative 24 fifteenths here. Okay, so I can do that calculation in my head, and I think that's right. Then if it's not, again, at least you're saying what needs to be done. Okay. Then I'm going to do negative of the third row plus the first row. Because negative 1 and negative 1 is going to give me 0. I'm going to get a 0 here. That's going to give me 1, 1, 0. It's going to give me 5 minus 117 over 15. Well, look at this. I've almost got my solution because whatever 14 minus 234 over 15 is, that's y. And that's negative 24 over 15 if I did it right. See how they compare. Got negative 12 over 5, so kind of close. Not going to ponder too much on my arithmetic, but not going to worry about that. Okay. Usually you're not going to have fractions like that in the problems you're assigned, although they can arrive. So I'm just debating. I'm tempted to change these numbers. Maybe 24 over 15. Well, let's just go ahead and do it. I'm losing track of my arithmetic here, but that's not that hard. So that should be negative 24 over 15. And 5 is 75 fifteenths. 75 minus 117 is negative 42. So that'd be negative 42 over 15. Of course, that could reduce just as this one could. So if I've got my arithmetic right, got that. Let's not worry too much about my arithmetic. It's worrisome enough to start with. Okay, so now all I have to do is add negative 1 times the second row here to the first row, and I have my solution. Because if I have negative 1 times this row to this one, well, 0 is not going to do anything. Negative 1 times 0 is 0, added to 1, still 1. Negative 1 added to 1 gives me 0, and negative 1 times 0 is still 0, added to 0 gives me 0. So all I've got to do is add the negative of this to this, and that's negative 18 over 15. This is negative 24 over 15 because it hasn't changed. And right there is my solution. This is x1 plus 0x2 plus 0x3 equals negative 18 over 15. 0x1 plus x2, I'll put the 1 in there, plus 0x3 equals negative 24 over 15. Okay. And 0, 0, 1 just means 0x1 plus 1x3 equals 117 over 15. In other words, x1 equals negative 18 over 15. X2 equals negative 24 over 15. And x3 equals 117 over 15. So by doing a couple more steps here, get our complete solution. And then we can check the solution, something you always want to do so you know whether you've done it right or not. I can plug these numbers into these equations and see if they work. Now, I suspect they might not. Let's see. But I'm just going to indulge me for a second here. 4x1 here would be negative 72 over 15. 6x2 would be negative 144. 72 to 144 is 226. Yeah. Negative 226 15ths. And then 8 times 117. Oh, what I have to do this? That's 880 plus 56, which is 936. Subtract 200 and what did I say? 226 from what did I say there? 956, not 926. And we get, well, we should get 15 times 48. Okay, 15 times 48 is 720. Kind of close. That's some indication that maybe this isn't too bad a solution. Of course, if it is, that means that there's something wrong with this one because they're not the same. It's the same system. Okay, let's take the third equation, which is much easier. Negative 18 and negative 24 is negative 42. Negative 42 and 117 is 75. 75 over 15 is 5. It checks out in this equation. Okay. And then here, I've got to do it. I'm sorry. Negative 90 plus 72 is negative 18. Plus 468 is 450. And 30 times 15 is 450, isn't it? I think I got it right this time. Makes me wonder what I did wrong over here, but obviously there was something. Okay, so the main thing is to understand that we can translate the system of equations into an augmented matrix, reduce the matrix down to this form where we have ones on the diagonal and zeros everywhere else, and we have our solution. Now this second solution just extended from the Gaussian elimination that we can solve using back substitution is Gauss-Jordan, or as Americans would probably pronounce it, Gauss-Jordan. And Jordan's a perfectly good name. Okay. So this is Gauss-Jordan, or Gauss-Jordan. I'm not trying to be all fancy and sophisticated with that Jordan pronunciation. That's what I heard in graduate school. So in undergraduate school, we did this. Okay. A little more terminology. This is row reduced echelon form. This is row echelon form. I never really knew what those terms meant. I didn't bother much with terminology, probably to my disadvantage. But there we have it. Okay. Now that's essential content of the first and second section of the text. So there are more details that I'll try to address in another video. And remember, we're kind of trying to make up for having lost 2/3 of our class time due to weather in the first week. And we do want to stay on track for your sake.